last time we have seen division algorithm, and corollary to division algorithm is your factor theorem. Factor theorem says an element A belonging to F is a zero of f of x belonging to capital F of x if and only if x minus a is a factor of f of x in capital F of x. So I would like to take you all to this screen. What I mean by capital F of x, let me just recall. Capital F of x takes all coefficients from the field F. F is a field. You are taking coefficients from F and you are forming a polynomial. Set of that polynomials we call as f of x, and it actually becomes an integral domain. Because the polynomials, some of the polynomials are not invertible, so it cannot be a field. So that is the only thing in case of f of x. Otherwise f of x would have been a field. Okay, now what we are saying is, if at all I say z2 of x, what I mean by this, all polynomials with coefficients 0 and 1 only. If I'm in z3 of x, all polynomials with coefficients 0, 1 and 2 and so on. So this is actually the meaning of f of x. So let us be back to the statement. An element A belonging to F. So A is an element of the field F. And A is a zero of your polynomial. Means what? F of A is 0. When it will mean that x minus a is a factor of f of x. And reverse way, if at all you find x minus a is a factor, means a is 0 of f of x. So we will prove it both ways. We are starting with necessary part. You will copy down these things in your notebook very properly. Okay, I begin with the necessary part. Let a belonging to f be a 0 of f of x. What I mean by this, f of a is 0. Now I would like to talk about x minus a. I want to show that x minus a is factor of f of x. Means what? I can divide by x minus a to f of x. So naturally the concept of division algorithm comes into picture. So by division algorithm, f of x when divided by x minus a, we will get some quotient and some remainder, of course, in our parent space f of x, such that small f of x is x minus a times q of x plus r of x, where r of x is either 0 or degree of r of x is less than 1. यहाँ पे हम फंक्शन, हमारी जो पॉलिनोमियल है f of x, उसको डिवाइड कर रहे हैं बाय लीनियर फैक्टर x माइनस ए. अगर हम x माइनस ए से डिवाइड कर रहे हैं तो हमें कुछ तो कोशेंट मिलेगा और कुछ तो रिमाइंडर मिलेगा. किसको हम रिमाइंडर बोलते हैं? तो या तो वो आइडेंटिकली 0 होगा या फिर उसकी डिग्री डिवाइजर से कम होगी. हमारा डिवाइजर है x माइनस 1, लीनियर है, उसकी डिग्री है 1, तो नेचुरली डिग्री ऑफ r of x will be less than 1. I suppose you followed me. So naturally a polynomial of degree less than 1 is nothing but a constant. So we will say that r of x is k, and what will be k? K will be a member of f. That is why I just now told you that whenever I am dealing with polynomials in f of x, all the coefficients are taken from f. That is what we mean over here. So this k will belong to f. Now this is statement we will rewrite as f of x is equal to x minus a times q of x plus k. Now we know how to calculate f of a. For that we have evaluation homomorphism. So we'll have evaluation homomorphism phi a from f of x to f. So phi of a applied on f will mean that it is f of a. How do we write it? We write it as phi a of f. And what is it? It is nothing but f of a. And because we have already stated that f of a is 0, what do I have? I get this to be 0 equal to this factor is 0, and we are just left with k, so k. So 0 is equal to k, meaning you got the value of k, that is 0. So the statement now becomes f of x is equal to x minus a times q of x. It itself means that x minus a divides f of x. Means x minus a is a factor of f of x. I suppose you followed me. Now reverse way I have to go. I'll say f of x minus a is a factor of f of x, and I want to reach to the fact that a is 0. So how will we go? Sufficient part. Suppose x minus a is factor of f of x in capital F of x. So I'll get f of x to be equal to x minus a into something. It is not necessary to write q of x. We will either write it as some polynomial g of x, something like that. So here we have written x minus a times q of x. Now again, whenever we want to reach to f of a, we have to apply the evaluation homomorphism. So same way, again we apply evaluation homomorphism phi a. So what I'm going to get? Phi a of f will be f of a, that is a minus a gives you 0. So a is a 0 of f. So it is so easy. This is actually corollary to division algorithm, and because it is giving you a factor, we call it as factor theorem. Now I would like to move ahead. Corollary. So what this corollary says, a non-zero polynomial f of x in capital F of x of degree n can have at most n zeros in a field capital F. It is but natural. All of you know this very well. This is actually the fundamental theorem in algebra. So if at all you have a non-zero polynomial of degree n, how many zeros it can have? It will have at most n zeros in F. How do we prove it? So suppose f of x is a non-zero polynomial. Suppose its degree is n. And we want to say that it has at most n zeros. If it does not have a zero, I don't have any problem. So no problem. So we start with how many zeros are there. So we start with if. Once again, concentrate to my statement. If f does not have any zero, we don't have any problem. So we are not discussing that case over here. No need to say. If at all it has a zero, then we count and we show that the number of zeros is smaller than n or at the most equal to n. That is the only thing we have. That is the only thing we have. So now, suppose a1 belonging to f is a 0. Then if a1 is a 0 of f of x, factor theorem says that you can have f of x is equal to x minus a times something. That something here we are denoting by q1 of x. Something. So q1 of x naturally will have degree less by 1. So its degree will be n minus 1. Do you agree? Are you following? Huh? Degree of f was originally n. I divided by linear polynomial. So naturally, degree here is 1 multiplied by something, and here it should be n. So what should I multiply it by? I should multiply it by n minus 1, then and then only. N minus 1 plus 1 will give me n. Do you agree?
Yes, ma'am.
Okay. So this is very natural thing. Nothing we did over there. These are routine thing. Okay, I erase this. Now, what will happen after this? I will be able to write f of x as x minus a1 into q1 of x. And degree of q1 of x is n minus 1. Again, I move ahead. Suppose a2 is also a 0 of q1 of x and a2 is other than a1. I forgot to write that here. A2 is distinct from A1. So in that case, what is going to happen? Q1 of x will be written as x minus A2 times Q2 of x. And what will be the degree of Q2 of x? Because Q1 is having degree n minus 1. Q2 should have degree n minus 2. Then and then only the left side will match with the right hand side. Because whenever you are writing two polynomials are equal, their degrees must be same. I suppose you are following. लेफ्ट साइड पे जो भी पॉलिनोमियल है हमारे Q1 ऑफ x है, तो उसकी डिग्री जो भी कुछ होगी वो डिग्री राइट हैंड साइड के पॉलिनोमियल से मैच तो होनी पड़ेगी, होना ही होगा. x माइनस A2 की डिग्री 1 है, तो उसमें Q2 की डिग्री ऐड करनी चाहिए, तभी तो प्रोडक्ट की डिग्री n बनेगी, आई मीन n minus 1 बनेगी. Okay, so what is your f of x then? F of x becomes x minus a1 times, here we have put the value of q1 of x, that is x minus a2 into q2 of x. So this way I can continue. Whatever number of zeros you have, accordingly I can continue. And suppose all the zeros are over now. I got a1, a2 up to ar. So suppose there are r zeros of f. So we got this equation which I have denoted by star. We can write f of x as x minus a1 into x minus a2 into and so on up to x minus ar multiplied by qr of x. And what is qr of x? So something, some polynomial. What will be its degree? N minus r, of course. Because whenever we talked about q1, we said degree is n minus 1. For Q2, we said degree n minus 2 and so on. So that is our notation. So as far as QR is concerned, its degree will be n minus r. And we are saying that suppose f of x has no more zeros, will mean that QR of x will also have no more zeros now in f. So equation star, what it tells you, degree of f is n. And on the right side you have r factors. So what this means, r must be smaller than or equal to n, because to this r you will add the degree of this particular. So what will be your r? R will be surely less or equal n. Now we want to show that these are the only zeros. For that what we did, we took b belonging to f, something else other than this a1, a2, ar. So if at all I'm having b belonging to f, and suppose b is distinct from those ai's, I have not taken a1, neither I have taken a2 nor ar likewise. So I have selected something else. B belongs to f, b is not ai for any of these i's. Now what happens? F of b becomes b minus a1 times b minus a2 times b minus ar into qr of b. And this will not be 0. Why it is not 0? Because QR has no 0. And these are distinct. So this cannot be 0. So what you got? F has no 0 divisors. F has no 0 divisors. So this cannot be 0. What do you mean by 0 divisors? Apart from not being 0, the product becomes 0. As if, if at all I had 2 into 3. I'm talking in Z6. What is this product in Z6?
0.
Yeah, it becomes 0. So that is what is known as 0 divisor. But here we are dealing with a f as field, and field has no 0 divisors, and so f has no 0 divisors. So this cannot be 0. What we mean to say is this value is non-zero. And this value is non-zero means b is not 0 of f. So only zeros of f are what? AIs. I running from 1 to r. So how many zeros are there? R zeros are there. And how is R? R is smaller than n. R can have maximum value equal to n. So what we have shown, f has at most n zeros in f. Got my point?
Yes, ma'am.
Okay. Now I would like to move ahead because you have this document with you. You can get it. Now I would like to go to the corollary. What the corollary is saying, if G is a finite subgroup, yesterday we were talking of this. If G is a finite subgroup of the multiplicative group F star comma dot. Why F star? So we are not taking 0. You know very well 0 is not invertible. We leave 0. Is it so? We always talk about non-zero elements to be invertible. So F star comma dot we have taken. Then G is cyclic. What I mean is finite subgroup of this multiplicative group is always cyclic. This we mean to show. The same statement we are saying in particular, the multiplicative group of all non-zero elements of a finite field is cyclic. Okay, so let us try to prove it. So I hope there is something kind of I would like to go back to the board then, and you can see whenever we talked about F as a field, what is F? F along with plus and dot we always talk. It is basically a ring. It is commutative ring. What do you mean by commutative ring? Anybody? Yes, with unity.
Unity 1, multiplication.
Yes, it is multiplicative identity. Yes, you are very correct. It contains multiplicative identity and it is commutative ring means what? I'm talking about multiplication. Multiplication is commutative in F. And what we have done from this F, we have taken its subset G. How is that subset? Finite. That itself, we are using the word finite. Is it so? We are taking finite subgroup of this multiplicative group F star comma dot. F star means what? We are taking it's 0. 0 element is omitted. So G doesn't contain 0 element over here. So we don't have any problem. So G can form a group with respect to multiplication. This is what we are saying. Okay. Now, so we want to show that this G is cyclic. Okay. So let us go ahead. F being commutative, the subgroup G comma dot is abelian. I feel all of you are quite familiar with this concept. F is commutative group with respect to multiplication. So it's a subgroup will also be abelian. Now, by the fundamental theorem of finitely generated abelian groups, what this theorem states? The statement is given here. Every finitely generated abelian group G is isomorphic to a direct product. So whenever you are having any finitely generated abelian group G, you can always talk that it is isomorphic to direct product ZD1 cross ZD2 cross and so on cross ZDR, where each DI is a power of a prime. So you may have like Z8. Z8, how would you read it? 8 meaning 2 cube. You may have cross Z27. What do you mean by this? 3 cube. And so on. So you are having powers of primes. D1 is a power of prime, D2 is a power of prime, DR is a power of prime, likewise. Are you following me? Come up.
Yes, ma'am.
Okay.
Power cubicच घ्यायचे का?
Not cubic. You may have 64 also. Yes. Z64. What Z64 means? It is 2 raised to 6. Is it fine? They are powers of prime. That is only what I meant to say. Ready?
Yes, ma'am.
Okay. Now, Let us suppose that ZDI is a cyclic group of order DI in multiplicative notation. So you know this very, very well, that ZDI is a cyclic group. You have studied this. So its order will be DI. So whenever I say Z5, what I mean by this is, yes, is a abelian group. Have you observed ever? Yes, it's a abelian group with respect to addition. Okay. And how many elements does it have? 5 elements are there. So it's a cyclic group of order 5. Okay. So same way here we are saying, let us suppose that ZDI is a cyclic group of order DI in multiplicative notation. So why we are saying suppose? Why suppose? So we are not challenging this suffix. What we are challenging is we want to say something next. For that we are saying suppose. Okay. Now see, what is the order of ZD1? D1. That of ZD2? D2. That of ZDR? DR. I feel you are following me. And now what I want is their least common multiple. What I want is their least common multiple. So how do you get least common multiple? Are you familiar with least common multiple? Suppose I'm
Yes.
having, yes, 4, 27, and suppose I have 25. How do I go for that? Okay, at this moment, I would like to deal with only 2. Okay, I have only 2. So what is their LCM? LCM we denote by square bracket. Okay, so what is their LCM? Can you tell me? Come on.
Only one, ma'am.
Actually, by GCD, what I mean divisor. And divisor is 1. You're very right. For divisors, we call it as 1. It is the greatest common divisor. But I'm talking about least common multiple. So what is the least number that comes in the tables of both? It's 100. It's 100. 4 divides 100, 25 divides 100. So 100 is the least common multiple of 4 and 25. Followed me? So actually, because we are dealing with the powers of primes, we have to take their product. D1 into D2 into and so on up to DR. Okay. And if M is the least common multiple, it is common multiple and it is the smallest amongst all the common multiples. Means what? M will be less or equal the product of all. Do you all agree? M will be smaller than every of these. What this means? M divides D1, M divides D2, M divides DR. Is it so? Is it so? Okay, okay, coming back. See, 100 is our M. In this case, 100 is our M. And 4 is what? 2 square. 25 is what? 5 square. Okay. So what I mean is, this 2 square, D1, does it divide M? Yes. 5 square, does it divide M? Yes, of course. That is why it is known as least common multiple. Sure. So in this case, what will happen? Every DI will divide M. That is what I have noted here. Later on, I noted it. So what do you see over here? M is smaller than the whole product. And AI belonging to ZDI will mean that AI raised to DI is 1. So naturally, AI raised to M will also be 1 because DI divides M. All right. I suppose you are getting me. Why for we have written this? Why for we have written this? Yes. So please, I would like to request you, go to your group theory books and check once what do we mean by cyclic group. How the things go on repeating and why for Yes.
It should have a generator.
Yeah, it has a generator, and this is the power. It's the power for when the value becomes 1, and because the value becomes 1, the same things are repeating over there. That is the actual scene over there. Okay, so I hope you'll visit your book group theory, and then you'll come to this concept. If not, I'm again here for you. Okay, do you agree?
Yes, ma'am.
Okay, only Pradna is ready. Okay, second. Okay, anybody else? Okay, Jyoti ma'am. Sure, you'll try. Then what is happening now? If alpha belongs to G, so we need to talk about every member of G. Then only I'll say it is cyclic. So if alpha belongs to G, then alpha raised to M is 1. Then every element of G is a 0 of x raised to M minus 1. You can watch over here. Alpha raised to M equal to 1 is a solution of what? X raised to M minus 1 equal to 0. Do you agree? In place of x, I put alpha. Alpha raised to M becomes 1. Alpha raised to M becomes 1. What this means? Come on. Alpha is a 0 of the polynomial x raised to M minus 1. Now, what is happening? G has D1. How many elements are there in G? This product. Because these many elements are with us. D1, D2, D3, N2, and so on up to DR. These many elements are there. So what will happen? It will have at most M elements because their LCM is M. So it will have at most M elements in F. And how is your M? You are saying these many elements are there, and then you are saying it has at most M elements, will mean that M is greater than or equal to D1, D2, DR. Here you said M is smaller. This is your statement. I hope you can recall. Is it? And here now you are saying that M is greater than or equal to this product, will mean that M is nothing but the product of these. Hence, the primes involved in prime powers are all distinct, and the group G is isomorphic to the cyclic group Zm. Okay, so this is the way. I hope you'll take it down in your notebooks, and then you'll come to know what I have said over here. So I suppose something you have got out of this. You'll try to read it once again. If not got, you can call me anytime. All right. Now I go to the irreducible polynomials. What do we mean by reducible polynomial? The polynomial which cannot be further factorized is known as irreducible. And the polynomial that can be factorized is called as reducible. How we are defining? The one which is not irreducible, that is said to be reducible. Only one thing I have to concentrate on, the wording over F. Irreducible over F and reducible over F. What I mean by this? So that we have already seen last time when we visited this. So I would like to tell you once again, okay, if I have this kind of polynomial, I hope you remember it. She's just now replied. X square minus 2 kind of thing. You know very well that this is not reducible in Z of X. Neither it is reducible in Q of X. But it is reducible in R of X. This we have already seen. Why it is reducible in R of X? Because I can write this as X minus root 2 multiplied by X plus root 2. So the coefficient root 2 is not integer, neither it is rational, but it is real. Hope you'll rejoin me. So this is the factorization in R of X. So we said it is reducible in R of x, but not reducible in these two. We call it as irreducible polynomial. So suppose you followed my concept. Okay. So here the coefficients are actually 1 and -2. They are both members of Z. So this polynomial is actually a member of Z of x. One more thing, you are watching Z of x is contained in Q of x, which is already contained in R of x. So Z of x is the smallest of all. It is contained in Q of x, and Q of x is contained in R of x. This you know better. So the concept of irreducible over f is now known to you. So we have a few kind of questions on this particular. Let us first deal with the theorem that will make it easy for us to decide. So this is a theorem. Let f of x belong to capital F of x and f of x be of degree either 2 or 3. Then f of x is reducible over f if and only if it has a 0 in f. So it's a quite good kind of result for us. F of x, if it has degree 2 or 3, we can immediately see if it is having a 0 in f or not. If it has a 0, then we can say it is it is reducible. It can be factorized, and if not, let it be. So it's if and only if kind of thing. So let us go for the proof. Then we'll understand what I mean is. We are going for the proof. We have taken f of x from f of x of degree either 2 or 3. Necessary part. So if f is a reducible polynomial, then we are talking. It is reducible means I can write f of x as product of two polynomials, g of x into h of x. Naturally, the degrees of g and h will be smaller than that of f. So the degree of f, we said it is either 2 or 3. So naturally, though it is 3, if I write it as a kind of product, then one of them will have to be linear. अगर f की डिग्री 3 होती है तो उसको प्रोडक्ट के तौर पे अगर लिखेंगे तो एक तो लीनियर होना ही चाहिए. And if it is 2, then there is no question as such. If it is reducible, if it is factorizable, then the degree of the factors have to be 1. That's very necessary. So suppose g of x has degree 1. Then what will happen? G of x has degree 1, then except for a possible factor in f, g of x is of the form x minus a only. What else? You will either write it as x plus k, but writing x plus k itself means that we are writing x minus k. So it is of the form x minus a only. And if it is having factor x minus a, will mean that g of a is 0. And if g of a is 0, then what will happen to f of a? F of a will also be 0 because your f of x is product of g and h. So it is g of x into h of x. I suppose you followed me. So if I put here a, then this will be a and this will be a, but this value is 0. So automatically f of a becomes 0. What this means? F has 0 in f. Followed? Okay. I would like to revisit this. यहाँ पे हमें f की जो डिग्री दी है वो either 2 है या फिर 3 है. अगर ऐसा होता है तो f reducible अगर है तो f should have a 0. और अगर f का 0 है तो f will be reducible. So we have to go both ways. Now in this case we started with f is reducible. अगर reducible है तो उसको हम product के तौर पे लिखेंगे. f of x is equal to g of x into h of x. अभी अभी मैंने बताया कि एक तो डिग्री 1 होनी ही चाहिए, आइदर g की होगी या फिर h की होगी. तो यहाँ पे हम मानते हैं कि सपोज g की डिग्री 1 है. अगर g की डिग्री 1 है तो इसका मतलब क्या है? इट इज अ लीनियर पॉलिनोमियल ऑफ दिस पैटर्न x प्लस k. तो यहाँ पे x प्लस के भी लिख सकते हैं हम, x माइनस के काइंड ऑफ थिंग. तो वही हमने लिखा है, इंस्टेड ऑफ राइटिंग माइनस के वी आर राइटिंग a. व्हाट दिस मीन्स? g ऑफ a विल बी a माइनस a विल बी 0. हो गया. तो इसका मतलब अगर यहाँ पे a डालते हैं तो क्या होगा? f of a इक्वल टू g of a इंटू h of a विल बी 0. दैट इज व्हाट आई सेड. मतलब क्या? f हैज अ 0. f 0 बनता है कहीं भी, तो f has a 0 in capital F. I suppose now you followed. Now I go to sufficient part. Suppose f had 0, then factor theorem helps us. If a is a 0 of f, x minus a is a factor of f of x. And if it is a factor itself, means it is reducible. So I suppose you followed the thing. Now I would like to go to the next theorem. If f of x belongs to z of x, this is very, very particular thing. We are talking about integral coefficients. Z of x means polynomials whose coefficients are integers. So f of x belonging to z of x, then f of x factors into a product of two polynomials of lower degrees r and s in q of x. If and only if it has such a factorization with polynomials of the same degrees r and s in z of x. Statement you should concentrate to. You have taken a polynomial from z of x, and what you are saying, this polynomial can be factorized into lower degree polynomials, but maybe the coefficients are from rational. When is this possible? It is possible if and only if you have similar factorization in z of x. What do I mean by similar? So suppose I'm having something like this, 2 by 3 x square minus 7x minus 11 by 5. Something like this, one factor I'm having. And another factor is x minus half. So you can watch these polynomials, they are in q of x. Their coefficients are rational. But I'm not watching to the coefficients, I'm watching to their degrees. This is my R. What is it? How much? R is come on. What do you find R as? And what is S then? How much is S? No? Okay, I would like to repeat the statement. See, f of x factors into a product of two polynomials, as I have said. यहाँ पे हम लिख देते हैं f of x is equal to, पहला polynomial कितने डिग्री का है? What is the degree of the polynomial?
2.
Yes, polynomial is of degree 2. That is what I said. R has value 2. And the second polynomial has degree
1.
1. So S is 1. तो F की कितनी होगी? You know very well, whenever we are talking about equality, so many times I have talked to you that the equality is very, very severe than that of the goldsmith. Have I said so? Huh? Goldsmith, whatever he is using that balance, R equality is severe than that one. It takes care of the equality, actual equality. So the polynomial f of x and the product on the right hand side have same degree. This degree is 2 multiplied by this particular. How much? X square into x
2
cube.
plus 1, 2.
So degree of this f of x will be 3. What we are saying, f of x is factorized into two polynomials. Naturally, if f is having degree 3, factorization will have smaller degrees, smaller than 3. So one will be 2 and one will be 1. So that the product gives me back polynomial of the same degree. I suppose now you followed. So R has value 2, S has value 1. What we are concentrating to is the degrees. So f of x factors into a product of two polynomials of lower degrees, we are saying R and S, in Q of x. The coefficients may be rationals. Okay. When is this possible? If and only if it has similar factorization. What do I mean by similar? So I mean I have something like x square plus bx plus c multiplied by x plus d. So what I have done? I have taken b, c, d as integers, and this product I have written back as my f. So if it is possible to write f in this fashion, then this is possible, and if this is possible, I can write this way. This is what we mean by this theorem. Okay, got this statement?
Yes, ma'am.
Okay, now I move ahead. No need of this proof because the proof is beyond the extent, but we are to use it. We will be using it, and that is why I explained. Now, in this corollary, you see f of x is nth degree polynomial in z of x. Means what? An minus 1, an minus 2 up to a naught. They are all integers. And we are underlining that a naught is non-zero, means constant term is not a zero there. And now, if f of x has a 0 in q, then it has a 0 m in z, and m must divide a naught. So here you need this particular theorem. This is actually corollary to that theorem. So let us see what is given to us. Once again, I revisit it. F of x is nth degree polynomial. Coefficients are all integers and constant term is non-zero. Okay. Now, f of x has a 0 in q means what? F of some p by q becomes 0. F of p by q value comes out to be 0. So if at all you are having such kind of thing, can you have such kind of thing? See, f of x is 2x minus 3. So what is the 0 of this particular? Can you tell me what is the 0?
Mm,
3 by 2. If I put x equal to 3 by 2, what will happen?
0.
Yes,
Answer will
f of 3 by 2 is 0. F of 3 by 2 is 0. I suppose you are getting me. So that is what we say. And then what will happen? This m, then it has a 0 m in z. So it will mean that m must divide a naught. So we are going to prove it. Just see. We have taken this polynomial. A naught is not 0. F of x have a 0 in a in q. What is the 0? Name is a. So by factor theorem, x minus a will be a factor. But this factor is in q of x. Why? Because we have taken it from q. So in q of x. We know that if f of x belongs to z of x, has factors of degree r and s in q of x, then f of x has factors of the same degree r and s in z of x. Just now we talked of the theorem and same is used. So what is going to happen? F of x has linear factors in z of x. So what will happen? F of x will have x minus m. M is integer. X minus m is a factor and something else you are left with. Whatever you are left with, you see, degree of f was n. So here I need to write the largest degree to be n minus 1. Then and then only this product will have degree n. One more thing, talking of the constant term, because you know very well, I would like to go here. See, if suppose I'm having x raised to 7 plus 10 x raised to 6, something like this, plus and so on. And the constant term I have is plus 3. And I multiply this particular polynomial by some x minus 7. What will happen? You know, the largest degree term will be x raised to 8 and so on. And the last term, constant term, will be constant into constant. So 3 into minus 7, surely I will have minus 21. Followed me? Whenever I multiply two polynomials, I first see to the largest term and then I see to the constant term. How do I get constant term? Constant means free from x. So it should be product of constant terms only. So the last term, the constant term, is going to be the product of constant terms. I suppose you followed. 3 into minus 7 will give me minus 21, which will be free from x. That is why I call it as constant term. Okay. So what is going to happen here? My term, the last term was a naught. In f of x, the last, I mean constant term was a naught. And here you see the first factor is having minus m here. So what I should have here to so as to get a naught? I want to say a naught equal to minus m multiplied by what? Yes.
Minus 1 by m.
Yes, of course, if I want plus, I have to multiply by minus. That is okay. And I want the answer to be a naught. M should be cancelled. So it will be a naught upon m. I suppose you got me. M's cancelled. Minus into minus became plus. I got a naught back. That is why here I am getting minus a naught by m. Followed me? Okay. And again you see m was integer. So we are in the integer coefficients, means we are in z of x. So every coefficient must be integer. And minus a naught upon m is also an integer, means what? When this will be an integer? When this will be an integer? Yes, come on. I have, suppose, value of a naught is, suppose, I have this to be minus 14. And upon, there is m. So what do you think? What will be the value of m? So that this will be an integer. Minus 14 by m will be an integer. For what value of m? For 1, sure. Yes, I do agree. Anything else?
Minus 1.
Minus 1 will also do. Anything else? I want m to be an integer.
2.
Yes, of course. For 2, for minus 2, for 7, for minus 7, this value will be surely an integer. Followed my point? So what I chose? I chose the divisors of A naught, divisors of 14. That is why you told me plus minus 1. Hope you agree.
Yes, ma'am.
Yeah. So what we mean is M divides A naught. This only we wanted to prove. M divides A naught. So the document is with you. I think you'll try. Okay. Now let me move to a kind of question. A question says, show that x raised to 4 minus 2x square plus 8x plus 1 in Q of x is irreducible over Q. Where are we? In Q of x. Q means rational coefficients. Actually, you may read this as integer, but we are in rationals. If at all you are getting answer of the kind 1 by 4 is accepted. If you are getting answer of the pattern 2 by 3 is accepted. Did you follow? So I want to show that I cannot reduce this in Q of x. So let us go. See what is the degree? Degree is 4. So what will be the kind of factorization? If it is factorizable, then what will be the kind of factors? So product of degree 1 and degree 3 or product of degree 2 and degree 2. That is the only possibility. How can you factorize degree 4 polynomial? Degree 1 polynomial into degree 3 polynomial or degree 2 polynomial into degree 2 polynomial. This is what you have. Suppose we deal with the first case. F of x has a linear factor, say x minus a. Then what will happen? X minus a is a factor in Q of x. So x minus m will be a factor in Z of x. I hope you agree. What is our theorem? Theorem helped us saying if at all you are having factors in Q of x, similar factors you will find in Z of x and vice versa. So you need to have x minus m as a factor over here. And what this means, this m will divide the constant term. Just now we have shown by the corollary. M must divide the constant term. So m divides 1. When is it possible? It is possible only in the case of plus 1 and minus 1. What are divisors of 1? Plus 1 and minus 1. Now, if I take plus 1, let me compute f of 1. What happens to f of 1? It becomes 8 and it is non-zero in Q. If you put x equal to minus 1, then you are getting this value to be minus 8. So again it is non-zero. So 1 and minus 1 are not zeros. 1 and minus 1 are not zeros of f of x. So such factorization is not possible. Got my explanation here? Yes, how many of you got it? None? All right, I would like to go back. यहाँ पे हमें एक पॉलिनोमियल दिया है और हम उसके कोएफिशिएंट्स जानते हैं, हम उसकी डिग्री भी जानते हैं. Coefficients are taken from rationals and constant term is 1. Keep in mind. When do I say, suppose I'm having f of x as x plus 1 in Z2. What is the zero of this particular polynomial? Yes, can anybody tell me? What is the zero? Huh?
Okay.
What are the members of Z2? Very small actually set do you have? 0 and 1.
0, 1.
If you put f of 0, the value is going to be 1. And if you put 1, f of 1 will be
0.
0. So this 1 is called as 0 of the polynomial because it is, the answer is 0. 1 is a 0 of this polynomial. By saying 0 of a polynomial means if I put in place of x that value a, then the answer should come out to be 0. Then a is called 0 of the polynomial. Followed? Okay. So when to say a is a 0 of the polynomial, if f of a becomes 0, we say a is 0 of the polynomial. And just now we have shown a is a 0 if and only if x minus a is factor of f of a. So x minus a times q of x. This is the value of f of x. And we say that f is reducible. It can be factorized. Okay. Now I would like to move back to our question. The polynomial was of degree 4. I said I can factorize this as polynomial of degree 1 into polynomial of degree 3 or polynomial of degree 2 into polynomial of degree 2. So we are dealing with the first case. One is having degree 1, the other is having degree 3. So we will not go with the degree 3, we will just be talking about degree 1 polynomial. Degree 1 polynomial will be of this pattern x minus a in q of x. Whenever it has factorization in q of x, at the same time we have same kind of factorization in z of x also. If I'm having linear polynomial in q of x, I get a linear polynomial in z of x. What is this actually? By saying linear polynomial in q of x means I have x minus a rational number. And x minus m is in z of x means x minus an integer. That is the only thing. Followed me? ओके यहाँ पे एफ ऑफ एक्स दिया है एफ ऑफ एक्स को अगर फैक्टराइज करना है एफ ऑफ एक्स की डिग्री 4 है तो फैक्टराइज करना है तो या तो आपको 1 डिग्री वाला मल्टीप्लाइड बाय 3 डिग्री वाला या फिर डिग्री 2 वाला मल्टीप्लाइड बाय डिग्री 2 वाला दीज आर द ओनली 2 पॉसिबिलिटीज यही पॉसिबल है तो हम पहली केस ले रहे हैं एक की डिग्री 1 है दूसरे की डिग्री 3 है तो दूसरा पॉलिनोमियल लेने में कोई यही नहीं है ना हम लीनियर ही हैंडल करेंगे तो हमने ले लिया एक पॉलिनोमियल जो लीनियर था x माइनस ए कहाँ पे था q ऑफ x में था मतलब क्या a रैशनल नंबर होना चाहिए a इज रैशनल लेकिन हमारा थियरम कहता है कि जब भी आप फैक्टराइज कर सकते हो q ऑफ x में तब आप उसी प्रकार का फैक्टराइजेशन z ऑफ x में भी कर सकते हो मतलब if you are having x minus a in q of x the same time you'll have a factor x minus m in z of x also तो यहाँ पे m क्या है इंटीजर है so we have taken x minus m followed this much only one hand okay so x minus m is a factor मतलब क्या m must divide the constant term अभी तो बताया था a naught is divisible by m divides a naught what was a naught constant term यहाँ पे constant term क्या है 1 है तो m has to divide 1 what are the divisors of 1 in integers divisors of 1 in integers only 2 divisors are there plus 1 and minus 1 so we have taken plus 1 Put x as 1. What happens? It becomes 8. You can calculate. 8 is not 0 in integers. Same time, f of minus 1 I calculated, it becomes minus 8. It is also not 0. Means 1 doesn't give you 0. Means 1 is not a 0 of f. Minus 1 is also not a 0 of f. Means what? This kind of factorization is not possible. Got me?
Yes, ma'am.
Okay. Now, go for quadratic into quadratic. F of x, suppose we write as quadratic into quadratic. Then what will happen? We have to equate the terms. If you are writing quadratic into quadratic in Q, same time you can write quadratic into quadratic in Z. So A, B, C and D, they are all integers here. You can watch. Now let me equate these two. So what I have done, I have actually multiplied x square into x square, I got x raised to 4. By quadratic, I multiply to linear, that gives me cube. So I got x square into cx as cx cube. At the same time, ax into x square as ax cube. So I have added them. Same time, x square multiplied by constant, x square multiplied by constant, and linear into linear. So I will be getting ac plus b plus d x square. Then how do I get linear term? To get linear term, there is only one chance, that I multiply by a constant term to the linear. So I got BC plus AD times X. And lastly, I'm getting the constant term. I suppose you followed. Next, what I did is term wise, I equated them. So you're watching coefficient of X raised to 4 is 1, same. X cube term is missing over here. So its coefficient must be 0. Quadratic term has a coefficient minus 2, so I must have this sum to be minus 2. Linear term has coefficient 8, so AD plus BC must be 8. And lastly, constant terms must be same. BD must be 1. If B into D is 1, B and D are both integers. So either B and D are both 1 or both are minus 1, but in any case both are equal. If they are equal, I can go with this particular statement. I'll write AD plus DC, or I can write this as AB plus BC. Anyway, I have taken B common. I'm left inside with A plus C. So what I got, B times A plus C is 8. Means what? If B is 1, A plus C will be plus 8. If B is minus 1, it will be minus 8. But here you have got A plus C must be 0. And at the same time you are getting these values. So this is not possible. So this is a contradiction. So this kind of factorization is not possible, and that is why f of x is irreducible over q. So I think you should take it down. You have now the PDF with you. So take it down and practice this. I suppose you followed me. Okay. All right. Now I will just mention the Eisenstein criterion. Actually, for practical, we have used this. What this Eisenstein criterion, it is actually stated in terms of a theorem. Theorem says, let P be a prime. Suppose you have polynomial of this kind, a n x raised to n plus a n minus 1 x raised to n minus 1 plus and so on up to a naught. This is in z of x, means every a is an integer. And an not congruent to 0 mod p means what? P does not divide an. What I mean by this statement, when p divides an, the remainder is 0, is not 0, means p doesn't divide an. But ai is congruent to 0 mod p for all I less than n. So for rest of the i's, ai is divisible by p with a naught not congruent to 0 modulo p square. Concentrate here. This statement says p divides a naught, but p square does not divide a naught. If it happens so, if you are able to find such a prime, then f of x is irreducible over q. In that case, f of x is irreducible over q. So you can go with this. P prime a polynomial you have taken. It is a member of z of x. An is not congruent to 0 mod p. For all i's, ai is congruent to 0 mod p, but a naught is not congruent to 0 mod p square. We want to show that f of x is irreducible over q. Again, we use the same fact. If suppose f of x is reducible, then what happens? So suppose f of x is reducible over q. Then f of x becomes reducible over z and has factors of the same degrees over q and z. So f of x is reducible over q. I can factorize this way, and on purpose we have taken the leading term as br x raised to r here and cs x raised to s. So you can see the factorization in terms of degree r and degree s. How will be r and s? Both will be smaller than n, then only this factorization is possible. And the leading terms should not be 0 then, and then only those will be called as degree. So this is what we have stated. Now how is the constant term? Product of constant terms is the constant term here. So we will get a naught equal to b naught into c naught. But you said b naught, a naught is not congruent to 0 mod p square. Will mean that b naught into c naught is also not congruent to 0 mod p square. Means what? B naught and C naught are not both congruent to 0 modulo P. One of them may be, but both at a time are not congruent to 0 mod P. So suppose B naught is not congruent, but C naught is congruent. Then what will happen? This is our given statement. So this actually implies us BR is not congruent to 0 mod P. CS leading terms, they are not congruent. So AN is also product of BR and CS. Now M is the smallest value of K. We are assuming that CK is not congruent modulo P. So we write this way. AM, this becomes the product, this particular sum, if R is greater than or equal to M. And whenever R is less than M, we get this kind of product. So actually here you have to multiply the polynomials, then you'll come to know what I said. Now, A naught, B naught is not divisible by P, Cn is not divisible by P, but the smaller ones, they are all congruent to 0 mod P, means they are divisible by P. So AM is not congruent to 0 mod P will mean that M must be equal to N. If M is equal to N, what do we get? Factorization is not possible. So it becomes irreducible. So I hope we'll take it down and we will talk of it if you require. So anything you want to say?